Alright, welcome. In this video I'm going to be telling you about some complex numbers. I'm going to start you off by showing you some equations that up to this point in this class we said we were unable to solve. So something like x squared plus 1 equals 0, if I tried to work at this, I'd get down to x squared equals negative 1, and if I tried to take the square root of both sides to solve this equation, I'd get x equals plus or minus the square root of negative 1, which up to this point we had said is not a real number. And with x squared plus 4, the same thing's going to happen. If we solve that equation, it's going to get down to the point where we're trying to take the square root of a negative number. And then also when we learned about the quadratic formula, we saw that sometimes when we applied the quadratic formula, say if I just happen to apply the quadratic formula on this equation right down here, the same thing could happen. I could be asked to take the square root of a negative number. So today what I'm going to ask you to do is just suppose we could, say we could take the square root of negative 1. And we're just going to, for argument's sake, call it I. Now I know we don't really have any reason to want to let the square root of negative 1 exist, and honestly in this course we'll only really see a couple of reasons why it would be helpful, but I think you just need to take it on faith from me if you believe me that if you start considering square roots of negative numbers, there's all sorts of other results that come out in mathematics that are interesting and, as it turns out much later on, less difficult than you would expect. Okay, so if we were to let I equal the square root of negative 1, we could kind of have a more definitive answer for these equations. The first one, the equation in blue, whose solutions were plus or minus the square root of negative 1, we could just call those plus or minus I. And over here, where we've got plus or minus the square root of negative 4, what I think you need to be reminded of is one of our radical properties. We haven't really talked a whole lot about radicals in this class, but we are about to in the next unit, is that, if I have inside of a radical negative 4, I could look at that as 4 times negative 1, right? And I can do that. And then I can say, okay, well, that's square root of negative 1, that's an I. So that's plus or minus, and then the square root of 4 is 2. And so that's, I could say plus or minus 2 of these i's. Okay? So it's kind of like a unit, kind of like a variable to your experience right now. And, obviously a person can do the same thing to the equation I solved in red and get 2 plus or minus 4i. I think at this point, though, it would be really important for me to point out, because it's something we're going to talk about again later in another lesson, is that much like irrational roots of polynomials that have, rational coefficients, these imaginary solutions, these things that have the square root of negative 1 in them, they come in pairs as well, these solutions to equations that are not real numbers. And we'll talk about that more a little bit later. Now that's going to pretty much be a good motivation for why we're going to be working with complex numbers in this class, but one important fact that I really want to emphasize before we go any farther is that if I is the square root of negative 1, then I to the 2 power is equal to negative 1. And we'll talk more about powers by at the end of this video, but that's just going to be really important for us, that I squared equals negative 1. Alright, now we're going to talk about complex numbers more generally. So that number that we just defined, I, which was the square root of negative 1, is what we would call an imaginary number. Okay. But we also saw, with that equation that we solved using the quadratic formula, that we sometimes could, add regular numbers to imaginary numbers. And so when we say a plus bi, that's, a is some real number like we're used to, plus some other number of i's, that's what we're going to call a complex number in this class. Okay? Now, all of the real numbers that you're familiar with are complex numbers. They've just got, 0 i's attached to them. And I is also a complex number. It's just got no real number attached to it. Okay, so the complex numbers is going to be just kind of a larger world of numbers now that we're going to be living in. And so the set of all complex numbers is called the complex plane. And so sometimes, you've seen the set of all real numbers written with that double back R. The complex plane, the symbol for that is the C with the kind of handwritten bold to it. Okay, so we're going to change the xy plane below to a complex plane and plot the points. So what we do is we label the x-axis as the real axis. Think about this like the number line, like you've been used to forever. And then the y-axis, that's going to be the imaginary axis. So that means that 1 is going to mean 1i now, 2 will be 2i, 3 will be 3i, and so on. And then okay, down here where y was negative, this is going to be the number of i's, negative I, negative 2i, and could go farther down there. Okay, so when we have the first number, z equals 2 plus I. Okay, maybe I'll just do that one in red. So that's over here to the right by 2. Okay, 2 on the real number line, plus I would be right up here. Okay, so yeah, let's put a little z there. W equals 1 minus 2i. Okay, so go to 1 on the real line, go down by 2. That's going to be the location of W. U equals negative 3. That's just an old-fashioned real number. That's going to go on the real number line, so it'll be right there. And then V equals negative I. That's what we would call a purely imaginary number. And it's just going to go down there. And so it'll be on the imaginary axis. That's what we were calling V. Okay, so that's how we would plot points in the complex plane. Before we move on too much, let's work an example. Okay, so let's solve some equations that have complex solutions. Okay, so I'm going to do the one in the middle, and then I'm going to have you try it out on the ones on either side, because I think that'll be a kind of a good mixture. So the first thing, all of these are having an x squared, no x term, so these are the ones we can directly solve. We did this a little bit in an earlier unit. I'm thinking I'm going to start by subtracting 80 from both sides of the equation in the middle. So I'll have 3x squared equals 5 minus 80 is negative 75. And then I'm going to try to solve for x squared and then take the square root of both sides. This is my idea. Divide by 3 and I'll get x squared equals negative 25, and I'll take the square root of both sides. And when I do that, I need to remember the plus minus. I'll have the square root of negative 25. Okay, we see the square root of a negative number. Now we need to know, okay, we're going to write this in terms of I. We're going to say, all right, I'm going to write this as square root of 25 times the square root of negative 1. Square root of negative 1, that's what we're calling I now, and so that's going to be plus or minus 5i. And that's how we're going to solve this, equations like this. So why don't you try this one on your own, the one on either side. Okay, so pause the video, work it, see if you can solve it, and then check your work against mine, because it's just going to pop up in a couple seconds. All right, there you go. So these two work the same. Okay, just say the only thing that happened different is the one on the right. We were taking the square root of a fraction, but we can do that. We've done that before in this class, and everything otherwise worked out the same. So this is how we were going to solve some equations, some pretty basic equations using square roots that'll come back with complex solutions. All right, the next thing is just kind of a couple of trivia facts about complex numbers. So if z equals a plus bi is a complex number, we usually use z instead of x for a complex variable, but we shouldn't be having to deal with complex variables at all in this class. It's really just complex numbers that show up as solutions to polynomial equations. Okay, a minus bi is what we're going to call the complex conjugate of z. And you would write that z bar, with a little line over it. And we've seen conjugate before when we were, just in the last unit, we were looking at irrational solutions to polynomial equations, how they came in conjugate pairs. I think that what I'm going to say about this is, if we have a number, this is a on the real number line, this is bi on the imaginary line, we've got this number z here. Z bar is just kind of like reflected across the x-axis somehow. And you don't really need to know a whole lot else about complex conjugate except just what it is for a given complex number. So if we've got z equals 3 plus 4i, z bar is going to equal 3 minus 4i. It's the number that's against I that gets made negative. So in this case, w bar would be positive 6i, and a bar, okay, well what we would need to do is we'd probably need to rewrite a. A equals negative 1 plus I. And so a bar will be negative 1 minus I. It's the number against the I that gets changed when you're computing the conjugate. And then the other thing is the absolute value of a complex number. And I'm just going to draw you a diagram real quick because I don't want to waste too much of your time with this. But the absolute value of a complex number, we're going to compute using the Pythagorean theorem. Okay, and if you look and you plot a complex number on the complex plane like I did on the left, and then you kind of look at it as a triangle, you can see that it's going to be one of these situations that observes the Pythagorean theorem, where a squared plus b squared equals the length squared, which means that the length is the square root of a squared plus b squared. Okay, so let's just do a little bit of finding the absolute value of these complex numbers. Alright, so the length of z, or the absolute value of z, not z bar, pardon me, the length of z is going to be the square root of 3 squared plus 4 squared. Or if you know about your Pythagorean triples, that's going to be a 3, 4, 5 triangle, so that length is 5. W equals negative 6i. Okay, so that's 0 minus 6i. So that's absolute value of w equaling the square root of 0 squared plus negative 6 squared. Okay, and this length is always going to be a positive number, right? Because we're squaring these real numbers that are the distances, right? A plus bi. Even if b was a negative number, okay, we're still going to square it and it'll become positive. So your absolute value shouldn't be an imaginary number itself. Okay, so that's going to be the square root of positive 36, and that's going to be 6. And then a equals I minus 1, that's negative 1 plus I. If I go to take the absolute value of that, that's going to be the square root of negative 1 squared plus it's 1i, so that would be positive 1 squared, and that would be the square root of 2. And that's how we find the absolute value of a complex number. Now here's just a little something I'm going to point out. Notice what happens when you multiply a complex number by its conjugate. So if z is something like, a plus bi, and we multiply z by its conjugate, which is a minus bi. Let's see, is that again? It's back where it's supposed to be. Okay, we haven't really talked about multiplying complex numbers yet, but I don't think you would be surprised to see that we pretty much multiply these like you would expect with FOIL, like with a distributive property. So this equals a times a is a squared. On the outside, I've got minus a times bi. On the inside, I've got plus a times bi. And the last two, I've got minus b, 2 b's, and 2 i's. Okay, this is going to be something that I need to work on right here, this I to the 2 power. And this is going to happen pretty frequently in this class. We're going to do something and run into an I squared and need to change that into a negative 1. We need to be able to recognize that. Okay, so what I'm going to end up with, once I subtract away those canceling terms and substitute I squared equals negative 1, is a squared plus b squared. And what's important about that is that this is a real number. Always. And this will be important when we go to divide complex numbers, okay? But if I take a complex number and I multiply it by its conjugate, that always gives a real number. And so just keep that in mind for later. All right, now the rest of this video, I'm pretty much going to be focusing on arithmetic with complex numbers. Addition, subtraction, multiplication, division, taking I to powers. I'm not sure if there's anything else. I think that's pretty much it. But we're going to really focus on the arithmetic here. So let's start by adding and subtracting. This also works just like you expect. What you need to think is combine like terms. So I'm going to say this is negative 2 plus 4i plus 3 minus 11i, where negative 2 and positive 3 are like terms that I can add together. And positive 4i and negative 11i are also like terms that I can add together. And then I could say, okay, this equals negative 2 plus 3 is positive 1 minus 7i. Just like if I was a variable, which in our discussion, it really is not. It's a constant, it's a unit, but you can treat it like a variable, like you're familiar with in our algebra class. And so subtraction also works the way you expect. You just have to be careful to distribute the negative to, the whole number. So I'm going to do that. I'm going to say this is 4 minus I minus 5 minus negative 8i is going to be plus 8i. Okay, and so then I'm going to combine like terms again. And I'll be left with negative 1 plus 7i. Okay, so that's, no, not the exact same number, but okay, I guess it's a coincidence. All right, multiplying complex numbers. Like I said earlier, it works like you expect. You just need to remember that I squared is negative 1. All right, so I'm thinking I might just do one of these for you and let you try the other 3 on your own and see if you know what you're doing. Okay. I'm going to do the one in the bottom left, the 5 plus 3i to the 2 power, because this is not going to be 25 plus whatever you think 3i squared would be, okay, negative 9. It's going to be probably more than that, so it's going to be 5 plus 3i multiplied by another 5 plus 3i. Okay, and I'm going to need to distribute that, so that's going to be 5 times 5 is 25, plus 15i, plus another 15i from the middle terms. And then the last two terms would give me a 9 and an I squared. Okay, I just need to remember that I squared is negative 1. And I can conclude that I have 25 minus 9 plus 30i, which is going to be 16 plus 30i. Okay. And I think I should also probably point out, and yeah, I can see that we're about to be talking about this later in the notes, that this form where we write the complex number as the real number first plus some number of i's, that's what we're going to call standard form in this class. Okay, so now I think you should try these other 3 multiplying complex number examples and try to get these down to standard form. Check your answer against mine. It's going to pop up in a few seconds. Alright, there you go. So I multiplied these all out. These all kind of came back to end up having something with an I squared that I needed to, rethink of as negative 1. And I was able to simplify down to A plus BI, some number plus some other number of i's. 10 plus 6i, 2 minus 39i, 11 plus 0i. I don't think I need you to write the plus 0i in my class, but, if you did have to write it in standard form or describe what the coefficients, A and B were, that would be 11 plus no i's. All right, yeah, I see why I did this. So before we divide complex numbers, we need to really just be certain, what do we mean by a simplified complex number in the first place? And we're going to say that that means standard form, which we just said was A plus BI, but it's not bad for me to just remind you about that. And we're just not going to have i's in the denominator of a fraction, okay, is what we're going to go for here. And that will help out. If we can just have a real number in the denominator of a fraction, then that will allow us to write a number as A plus BI. And I think I'm just going to ask you to let me show you why that's true here in a minute. Okay, but first we're going to simplify the complex number. We're going to write the complex number in standard form. So maybe I'll do the first one and the third one because they look kind of the same. Or they look the same as the second one and fourth one, respectively. So I'm going to say 2 minus, okay, like earlier I was calling that the square root of 25 times the square root of negative 1, and saying, okay, the square root of negative 1, that's what we're calling I now. So this is 2 minus 5i. Then over here, if I'm dividing both 4 and the square root of negative 12 by 2, then that's like multiplying it by a half. So that's like half of 4 minus the square root of negative 12. And I might call that half of 4 is going to be 2, if I was to distribute that, minus just half of the square root. But I might call that the square root of 12 times the square root of negative 1. And then I'm realizing, if I'm going for like really simplified radical form, I should probably get at that 12 because I know that 4 divides 12. So I know that I can write 12 as 4 times 3, and I might just kind of go in there and say this is the square root of 4 times the square root of 3 times the square root of negative 1. So now I'm going to have 2 minus half of 2 square root 3i. And then, half of 2 is 1, so this is 2 minus the square root of 3 times I. That was kind of a lot, but, that was a good one. So why don't you try it on your own with these other two and see what you get. I'm going to pause, write in my answers, and you can check your answer against mine here in just a couple seconds. Alright, there you have it. Okay, so these kind of were mostly the same. They kind of had a radical that ended up hanging out, but otherwise they worked pretty much the same as the other one. So we just need to be very cognizant of standard form, kind of throughout this whole unit. Alright, now dividing complex numbers, this is going to be, a little more labor intensive is what I would say. It's not just as easy as dividing two real numbers, but it's not that much worse either, especially once you do it a few times. So what we're going to do is we're going to look at these situations, 1 over I and 1 over 2 plus 3i. I'm just going to show you a little trick. So what I'm going to do is I'm going to multiply 1 over I by I divided by I. And we know that if we multiply something by, or we divide something by itself, that's like 1. So if I'm multiplying by I over I, I'm not changing this number. I'm just multiplying it by, a clever form of 1. So on top, I multiply 1 times I, and that equals I. On bottom, I have I times I, which is equal to I squared. And now we know that I squared, we've been highlighting that in yellow and calling that -1. So this is I divided by -1. We know what happens when you divide something by -1, it just makes it negative. So this is -I. Okay? And that's how we would divide 1 divided by I. Okay. 1 over 2 plus 3i, we're going to need to be a little more careful. And I don't know how you would know to do this besides me telling you, but I'm just going to tell you. We multiply by a clever form of 1, and that form of 1 is the conjugate of the denominator divided by itself. So if I've got 2 plus 3i in the denominator, I need to multiply this by 2 minus 3i divided by 2 minus 3i. And we'll get to the point, here in a second where we're going to, you can even see down below the examples, we're going to do complex number divided by complex number, and still the same will hold. We're still going to multiply on top and bottom by the conjugate of the denominator. Okay, but I think I probably should zoom in a little bit on this because it's going to involve some computation. Now when I go to multiply the numerator, that's just not going to change because I'm multiplying by 1, so 2 minus 3i. But in the denominator, I'm going to multiply 2 times 2, that's 4, 2 times -3i, -6i, positive 6i, and then the last 2 would be 3i times -3i is -9i squared. And remember, that's why I showed you earlier what happens when you multiply a complex number by its conjugate. That you always get a real number back, right? That we saw that these numbers are going to cancel, -6i and positive 6i, and then we're always going to get that I squared, which is a -1. We can say, all right, this is 2 minus 3i divided by 4 minus 9 times -1. Okay, so that's divided by 4 plus 9 is 13. And if I need to write that in standard form as some number plus some number of i's, so I'm just going to divide both of those numbers by 13. And that's how I would write this in standard form and do that division. Really just emphasizing that when dividing complex numbers, really what we're doing is we're multiplying by the conjugate of the denominator on top and bottom so that we're not changing the number, we're multiplying by 1, but we're allowed to kind of work it into standard form, which I've got highlighted in gray there. All right, now this is something you need to practice on your own. Okay, you can watch me do this all day long, but it's not going to be as good as you doing it yourself. So I'm going to pause the recording and work all 4 of these divisions myself, and you can check your work against mine. I'm really encouraging you here to pause the video, work these on your own, give it a good, honest effort, see where you're at, and then check your work. Don't just copy off of my answers when they pop up here in 5 to 10 seconds. All right, here we go. First, I multiplied all of the fractions on top and bottom by the conjugate of the denominator. Multiplied it all out, applied I squared equals -1, did a little bit of simplifying, and got it down to standard form. Okay, so that's how we're going to divide complex numbers, and this is something you just got to practice. All right, now a quick interlude before we go on to the next thought, which is taking I to various powers. I'm just going to kind of a question for thought. If we've got f of x equals x squared plus 4x plus 5, what's the value of f of -2 plus I? So I think what I'm going to do is I'm just going to show you what I mean here. F of -2 plus I, that's where I just plug in -2 plus I for x. So it's going to be -2 plus I, not -2i, -2 plus I squared plus 4 times -2 plus I plus 5. And I could do a little bit of work with that, so that'd be -2 plus I times -2 plus I. I could distribute the 4, so it'd be plus -8 plus 4i, and then plus 5. And then if I was to go and, actually square this, I get -2 times -2 is positive 4. negative 2i minus 2 more I, and then plus an I squared, and minus 8 plus 4i plus 5. Okay, so I would need to kind of collect all of the real numbers together, remembering that I squared is a real number, it's negative 1. So it would be 4 plus negative 1 minus 8 plus 5. Where that negative 1 right here is from that I squared. And then I could put all the complex numbers together, so it'd be minus 2i plus 4i. And if I started to collect all the like terms, I'd see that I get 0 plus 0i. And so that's just going to be 0. And so I think what I'm trying to show you here is that negative 2 plus I is a 0 of f of x, or it's a root. And we'll talk extensively about complex roots of polynomials as we move forward through this unit. All right, now the last thing I got to tell you about is how to take powers of I, like I to the 5th, or I to the 25th, or I to the 105th. We might be interested in different powers of I, at least in this class. So I think what I need to remind you is what I told you about at the very beginning of this video, and that's that I is the square root of negative 1, and I to the 2 equals negative 1. Okay, so that's going to be, I'm going to fill in my first row of my table with that. I to the n is I to the 1 equals I. Okay, that's nothing I can do with that. That's the square root of negative 1. Okay, I to the 2 is equal to negative 1. Okay, that's just kind of two things that we've already agreed upon so far in this video. I to the 3, I'm going to do a little bit of work off to the side. Okay, something we know about exponent properties is that I could write I to the 3 as I times I times I. Right? And then I could just grab two of these i's, and I can make an I squared times I. And we know what I squared is, that's negative 1. And so this would be negative 1 times I, and that would be negative I. So that's why I to the 3 is going to be negative I. Okay, now I to the 4, I'm going to just propose that that's positive 1. I'll just show you why off to the side. All right, so I to the 4 is, I'm going to just propose that that's I squared squared, right? That we know that exponent property, that's how exponents work. If I'm taking power of a power, that's where I multiply the exponents. And we said throughout this video that I squared is negative 1. Okay, and we know what happens if you multiply negative 1 by negative 1, if you square negative 1. We're going to get positive 1. Okay, so that's why I to the 4 is equal to 1. Okay, and then kind of going on after that, I to the 5, I could say I to the 5 equals I to the 4 times I to the 1. It's just 1 bigger than I to the 4. And we said I to the 4 is 1. I to the 1, well, that's just I. So it's going to be I. And what happens is it cycles back through. It's going to be I, negative 1, negative I, and then positive 1. And what this means is that, if you're taking a power of I that's a multiple of 4, that's going to be 1. And that's going to be key to finding these, kind of more abstract powers of I, like 76 or something like that. Is it divisible by 4? Or, where is it in relation to the nearest divisible by 4 number? Okay, but before I do that, I kind of want to go the other direction, because I just looked at positive powers of I. What if we looked at negative powers of I, right? We've learned about negative powers in this class. So if n was equal to, let's say, negative 1, okay, I to the negative 1 is equal to 1 over I. But we could also kind of just think about this on the table. It's so repetitive, you would think the power or the pattern would just keep repeating. So, if I go, what do I go up by from I to get, up here, that would be, wait, that's not right. Hold on. Oh, yeah, I missed one. What's 1 less than 1? That would be 0. I to the 0 would equal 1, and that makes sense based on what we've learned in this class. I to the negative 1, okay, that would be the one that's above 1. I was like, oh, it's not supposed to come back 1. That would be negative I, and we actually, I believe, already showed that in this video. Yes, we did, right back up here. That 1 over I was equal to negative I, and that I could also just say that, okay, 1 over I, that's the same as I to the negative first power. And then if I wanted to, I could just kind of keep this going and say negative 2, I to the negative 2 is going to equal, oh no, what's going on here? Okay, nothing good. I to the 0 equals 1. I to the negative 2 is going to be negative 1. And then I believe I to the negative 3 would be positive I. Okay, but I don't have room in my shot to keep going, and you could do that if you wanted. It would just continue following the pattern. All right, so these examples, I think I'm going to just do one of them and have you try the other 3 on your own, so I can get you out of here. I'm already over half an hour, and I try to keep these videos under that. What we're going to do is we're going to think about, okay, we're taking I to the, say, 42nd power. We think about what's a nearby number near to 42 that's divisible by 4. And so I would say 40. Okay, so I'm going to write out I to the 42 is going to equal I to the 40 times I to the 2. Because I know about the addition property of multiplying two numbers that have the same base and different exponents. Okay, I to the 40, I'm going to rewrite that. We can always write that as a power of I to the 4. Okay, so that's I to the 4 to the 10th power. And I just showed you why I to the 4 is always equal to 1. So we're going to take that and we're going to say this is 1 to the 10th power times I to the 2. And we've been saying throughout the video that I to the 2 is negative 1. And so I've got 1 to the 10th times negative 1. That's negative 1. Because any power of positive 1 is positive 1. Okay, so why don't you try the other 3? Okay, what's the value of I to the 107? Okay, I think 100, that's divisible by 4, but there might be one even closer. I to the 89, I to the 172. Try these on your own. Try to find numbers that are nearby and, able to be multiplied by 4. I don't know, 172 sounds kind of hard to me, so I might show you different techniques. But try this with the video paused and then check back in a couple seconds. Alright, there you go. So, on each of these I tried to find a number that was nearby that I knew was divisible by 4. And so, I was kind of thinking, putting myself in y'all's shoes, and I was thinking maybe they don't know 104 is divisible by 4. But I know that y'all all know that 100 is divisible by 4 because you know that 4 quarters makes $1. Okay, I know you know that. So, that means that I could start off with I to the 100 and then say I had 7 left. And then I could do 4 and 3 like that. Okay, so that's an option that you have. And same with I to the 172. I think that's why I chose that, was that I was saying, okay, well, I think we all probably know that 160 is a number that's divisible by 4. Okay, and then we think about how much we have left. Okay, there'll be 12 more powers of I. Okay, both of those numbers are pretty clearly divisible by 4. So I've got, some power of 1 multiplied by some other power of 1. And that's going to be 1. Okay, so I think that's all I got for this video. Thanks for watching. Hope it helped. Get yourself some practice on the practice problems.